All right, guys, welcome to our topic on what's called equilibrium. And you guys could write that would sound like there's going to be something that's equal here, and we're gonna talk about exactly what equilibrium is. We're also going to introduce this term reversible reactions. It's a different kind of reaction than perhaps what we're used to. For example, you guys were to look at this, right? You guys know on the left side of the chemical equation we have the reactants, on the right side we have the products. Just looking at that, I want you guys to think, what just kind of looks different than what you guys have seen previous? Hopefully you guys would recognize you see a double arrow. You've got an arrow going to the right, an arrow going to the left. What that would describe is a reversible reaction. And reversible reactions can take place in closed systems. For example, like if I had this flask, I have water in it, I remove the stopper, this would be considered an open system. And you think about it, what's happening right now? I mean, we can't really see it immediately, but we would know if I leave this sit for a significant amount of time, I'm going to have less water than what I had originally. Because what's happening is, you guys know, some of that water is evaporating. So we really have a reaction or a process going one way. We have it going from liquid water to gaseous water. Like if I were to write that, I would write, right, H2O, H2O liquid going to H2O gas. Right, you guys see starting reactants are what we start with, products are what we end with. Well, now look at this. Now what if I put the stopper on? Now all of a sudden I have what's called a closed system, and that changes the process. Now, not only do I have liquid going to gas, that is evaporation, but you guys know what else is happening. Not only are the liquid molecules becoming vaporized in the gas state, but aren't some of the water vapor condensing back into a liquid. And so we have what's called a reversible reaction. Liquid's being vaporized and the gas is being condensed, and that would explain why if I let this, right, if I close this up, if I come several days later, wouldn't I have the level of the water would be slightly lower, indicating some of the gas is vaporized. But unlike in the open system, where if I were to come a week later, all this water would be gone because all you have is the evaporation process. With it closed, ultimately I'm going to reach a point at which the level of the water stays constant. And now when it stays constant, the misconception is the water molecules stop moving. That's not the case. Eventually, the amount of water will be constant. What's happening is evaporation is still occurring, right? And you think about it, initially, which process is happening the fastest? Evaporation, right? But then as gaseous water molecules build up in the gas phase, more and more of them, right, you would realize, right, wouldn't it be the slower moving ones that kind of reattach, condense back into a liquid? So then, eventually you're going to reach at a point at which the same amount of water molecules are evaporating as are condensing. So if I have just as much going this way as are going this way, ultimately, what's the result? Wouldn't the concentrations of these remain constant? Okay? And you think about it, that's what we're talking about when we say equilibrium. Equilibrium does not mean we have equal amounts of my liquid and my gas. Equilibrium would indicate that the rate of the forward reaction, we've reached equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. We're going to try to help explain this a little more here soon. Okay, I'm going to come to that. All right. Okay, so I want us to think about it. We're going to have this little hypothetical situation. Let's say you were looking for a job, and a good job might be working at a golf course. What could you do at a golf course? You could be the one responsible for going around and picking up all the golf balls, right? So let's say they assign you guys, in fact, I'd actually want you to draw this for your notes. I know it looks kind of hokey, but let's say it's this kind of modified container vehicle. Let's say this is in your vehicle, and this is the container you're going to use to collect your golf balls. But it's so designed, so it's like it's enclosed, okay, kind of representing a closed system, where it actually has two levels. You have an upper level and a lower level, okay? So let's say when you're going around collecting your golf balls, let's say, right, a chute opens in the back, and that's where you throw your golf balls in, okay? So let's say you go out, you collect a bunch of golf balls. let's say on day one you collect 1,000 golf balls, okay? You put all your golf balls in on this upper level, okay? Now, what do you guys got to do with the golf balls? You got to bring it to the distribution center. But let's say you're at like some ghetto golf course that has a bunch of gopher holes. It's not the best, most smoothest ride. So you're just kind of bumping in your golf cart. And in your golf cart, you're hearing in the back, right? What are the balls doing? You guys can imagine. The balls are just bouncing all over the place, right? Because it's kind of a bumpy ride. So then I would ask, you would get to the distribution center, you would open up the back, and what would you find? When you guys imagine, when you guys expect to find golf balls in both levels? Well, let me ask you guys, what do you guys think? Just look at how it's drawn. Where do you think you might find the majority of golf balls? Wouldn't you guys agree that when you expect to have more golf balls on this bottom level? And you guys think about it, here's the reason why. Golf balls are just kind of moving randomly. You guys, this is kind of like into a chemical reaction, right? You guys remember there's a rearrangement of atoms, okay? Well, you think about it. Golf balls are going to be able to go to the right. You can imagine some of them are going to go to the right. You guys, what am I likening that to? If they go this way. I'm likening that to the forward reaction. You guys remember going back to this? You guys remember with the reversible reaction? So I'm likening that to a reversible reaction. Remember, the forward reaction is when the reactants rearrange and then form products. And then the reverse reaction is when the product side goes to the reactant side, okay? So when the golf balls go this way, that's like likening to the forward reaction. And then you guys can imagine, but you guys remember they're bouncing. Just because they end up here doesn't mean they stay there. Wouldn't you guys agree? Golf balls are going to be bouncing back and forth. And so if they go back this way, that would be an example of what's called the reverse reaction. Okay? Now you guys think about it. Why would it be right to predict more golf balls here at the lower level? Wouldn't you guys agree? Because which way is it easier for the golf balls to go? To the right, the forward, or the left, the reverse? Oh, and then just to be clear, wouldn't you guys, just to kind of follow our analogy, wouldn't these be likened to the reactants? And these would be likened to the products. The reason why you would expect more on this side, wouldn't you guys agree? Because they're going to be able to go to this side if they overcome this hump. You guys think about, what's that hump like? What are we likening that to? That's our E sub A. You guys remember our activation energy from the previous unit? Remember, atoms have to have enough kinetic energy, right, in order to break old bonds. And so they have to have that minimum amount of energy in order for the reaction to happen. So we're likening that hump to the activation energy. And when you guys agree, the activation energy going this way is much lower than, now imagine them going the reverse direction. Now what's the EA? They actually have to have enough energy to overcome this larger hump. When you guys agree, the hump is less going to the right than it is to the left. So that would help us to understand why we might expect more balls to be over here on the product side than we would expect them to be on the reactant side. So, what might be a good amount? I don't know. Wouldn't you guys predict just how it's drawn? Maybe I'd have about 400 balls here. Remember, there was 1,000 balls. Maybe 400. When I get to the distribution, I count 400 here and maybe 600 here. Right? Doesn't that seem reasonable? Now, okay, we're going to continue with our analogy. Let's say you get to the distribution center, and then the boss says, "No, George." Let's say George, you're not supposed to go here. You're supposed to go on the other side of the golf course. So George, he doesn't care. You're making you're getting paid by the hour. Like, okay, so you get back in your car. You got your bumpy ride. You're driving all the way back across the golf course to go to the other distribution center. You can hear the balls bouncing all crazy in the back, and you're just, okay. Then you get to the end, you get to the new distribution center. Then I would ask, how would you expect the distribution of balls to be? How many would you guys, we're just speculating. How many balls would you guys expect to be here? How many balls would you expect to be there? It's kind of a trick question. Just because you got in your car and you went again, would you expect there to be any different? I would still expect, based upon the height of the shelf, I would still expect about 400 balls here and 600 balls here. Would it be reasonable to conclude that if you counted after you drove again, that there's still 400 here, just like before, and 600 here, would it be reasonable to conclude that all the balls just stopped moving? No, you could hear the balls moving. You knew they were moving. So what would explain why there's 400 here and 600 here? We would say we've reached equilibrium. Basically, we've reached equilibrium, and you guys remember that we know we've reached equilibrium when the concentrations or the amounts don't change. And what would explain why those don't change? A reasonable explanation is not that the balls stop moving. We would still have 400, 600 here if the rate of the forward reaction, right? Let's say, every second 10 balls are going this way, but then every second 10 balls are going this way. Wouldn't you guys agree if you have just as much going this way as going this way, what's going to happen to the amounts of those or the concentration of those? They're going to stay constant. That's when you say you've reached equilibrium. Remember, what does equilibrium mean? Remember, when you guys think equilibrium, you think it's something is equal. Equilibrium does not mean you have the equal amounts on both sides. That's not what equilibrium. You've reached equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. So if these don't change, we know we've reached equilibrium. Guys, we're going to do a different scenario. Let's say on day 2, okay, let's say you did such a good job, they call you back, day 2. But let's say there's not as many golf balls on day 2, you still have to go out and collect it, okay? So let's say it was only 500 golf balls, okay? So you put 500, and you guys, let's just say, you guys, and really, I'm thinking you guys would recognize, it doesn't really make a difference whether you put all the golf balls here or all the golf balls here, you put some here and here. When you get in and you're just bumping, those golf balls are just kind of moving randomly. But now on day 2, we have 500 golf balls. Remember, day 1 was 1,000. So let's say we're driving around, going all over the golf course. We've got 500 golf balls. We're hearing them banging. And then we reach the distribution center. What would you guys expect the ratio of balls to be? Once again, we got the same truck. Once again, is there any reason to expect anything different when we still expect more golf balls to be here? Once again, because it's easier to go to the forward direction than it is to go in the reverse. So you guys, I want you to pause here and think, what do you guys think? How many golf balls would you predict on both sides? Would it be reasonable to predict? Oh, we'll probably have 200 here, maybe about 300 here. And you guys, I'm just trying to use easy numbers to help us to understand. Now, what I want you guys to hopefully see is, and this is what chemists have figured out, and this is kind of an analogy. Can you guys figure out what stayed the same between day 1 and day 2? What stayed the same? Obviously, we used a different amount of golf balls, but something stayed the same. Hoping you guys would see. Didn't what stayed the same is the ratio of products to reactants. And this is what chemists have found with reversible reactions. Once a reversible reaction has reached equilibrium, the ratio of products to reactants stays the same. Notice the numbers don't stay the same. The numbers are different, but the ratio is the same. Now, for example, look. So this is what we're going to put. We call this an equilibrium. Whenever we use a big K, we use a big K in chemistry to represent a constant, something that doesn't change. So we're going to see something that doesn't change. It's the ratio. So I'm going to call this KEQ, which is the equilibrium constant. So what's constant here? It's the ratio of, you guys, whenever I use a brackets, that means concentration. It's the concentration of the products to, you guys know when you do a ratio, you can write it like a fraction. This is saying the ratio of products to reactants. That stays the same. Check it out, right? So if I was to calculate the constant for this, I'd get my concentration of my products. Let's say day 1. Let's say it was 600. Okay, now that's not really a concentration, it's a number, but we're just kind of working with it. And then compared to the reactants, how many reactants on day 1 was 400? You guys, what is the ratio? We could reduce that down. You could cancel out the zeros. Wouldn't that be, it's a 3-to-2 ratio. And you could even put it as a whole number, it's 1.5. That's the ratio of products to reactants. Now look, we said the ratio of products to reactants is a constant. You remember that's what big K is. It stays constant regardless of how much you have. It's always going to stay the same. It's all based upon how the activation energy is going forward and reverse. Notice that's the one thing we didn't change. We have the same construction here. So now look, the only thing we changed on day 2 was the amount of golf balls. But now let's look. The numbers change, but now check this out. Let's calculate the products to reactants. What's the products on day 2? 300. What's the products, I'm sorry, the reactants on day 2? 200. And I think you guys can see it. 300 divided by 200. Can I reduce that down to 3/2? And what do you see? It stayed the same. It's 1.5. That's what they found is the case with reversible reactions. That's not working too well. I'm gonna try to show something here. Guys, hold on one sec. Just going to. Okay, sorry guys. Okay, so you guys, this was kind of an analogy to help us to understand on a chemical level. So now we're going to revert actually to some chemistry. Okay, so you guys will write this down. This is kind of representing a generic equation. Okay, see how it's just a generic equation. This is, once again, on the left side are my reactants, those are my products. You guys see the lowercase letter, those are my coefficients. You remember the numbers in front? And then the uppercase letters are representing the reaction species, the substances that take place in the reaction. Okay, so then, remember what we said, and you notice you'll recognize it as a reversible reaction if you have a double arrow, okay? So then, you remember what we said stays constant, regardless of how much reactants and products you have. Once it's reached equilibrium, you'll take you remember it's the concentration of the products, you guys see that goes on the top in the numerator, over the concentration of the reactants. That's kind of what we like with the golf balls. And they found that this always holds true. If you take the concentration of your products, and now notice, look, it's raised to the power equal to whatever the coefficient is. So whatever numbers here are here, you're going to raise it to that power. And they found whenever you do that, you're always going to get the same value every time. I'm going to kind of show you how that works. Okay, so you guys, here's a reaction. Once again, we have a reversible reaction because I'm going to show you guys. So you guys write this down. We have hydrogen reacts with iodine in a reversible reaction to produce hydrogen iodide. This is kind of what I did. I don't know if you guys can see this. Hopefully you guys can see it's purple. There's like a purplish gas. You guys see what's causing the purplish gas? It is iodine. Iodine is purple when it's in the gaseous phase. It's purple. So what I did in my flask, I'll show you guys, is so it's at 445 degrees Celsius. So I have it on a hot plate. It's at 445 degrees Celsius. I added 1 mole of hydrogen and I added 1 mole of iodine. I put 1 mole of hydrogen, 1 mole of iodine. And you guys can see it's purple, okay? So, I just did that just before the video, okay? And so you guys can see what's gonna happen is, some of the hydrogen and iodine are gonna collide. You guys remember, molecules need to collide. And if they have enough activation energy, you guys remember, high enough kinetic energy to collide, such that old bonds can break and new bonds can form. Old bonds break, they can, hydrogen and iodine can combine together and form hydrogen iodide. That would be our typical reaction, okay? But, you guys notice, this is in a closed system, okay? So what else can happen? Can't some of the hydrogen iodide molecules collide and then break up back into hydrogen and iodine? And you guys think about it, eventually, okay, so we have this reaction going right here. Eventually, it's going to reach equilibrium, okay? And you guys remember, what does equilibrium mean? Equilibrium doesn't mean I end up with equal amounts of my reactants and products. Equilibrium means that's the point at which the rate of the forward reaction is equal to the rate of the reverse reaction. So the question is, how am I going to know when equilibrium is reached? Now you guys will notice, I don't know if you guys are seeing right now, remember, this was a lot more purple. In fact, I think maybe you guys can see it over time. It was really, really purple. But you guys can see now it's becoming less and less purple. And why is that? Because isn't some of the hydrogen and iodine combining to form this, and so therefore the concentration of this is becoming less and less. Well, how am I going to know when I've reached equilibrium? You guys remember what that means is, I have just as much going this way as is going this way. And when you guys agree, if you have just as much going this way as going this way, wouldn't the concentration of all these stay constant? And what's the easiest way I could view? How would I know when I've reached equilibrium? Well, when I look at this and I don't see the color changing anymore, right? What was I seeing the color change initially? It was becoming less and less purple, right? Because some of this was being used up combining with this. But once I reach a point at which I see the color is not changing anymore, that indicates, okay, I've reached equilibrium. That means that the concentrations of these are staying constant. Okay, so then here's the type of calculation you might have to perform. So once again, we added, let's say it was a 1 liter container, that was not quite 1 liter, but then I added 1 mole, so it's 1 molar. You guys remember molarity is moles per liter. So if I added 1 mole to a 1 liter container, it's 1 molar. So initially, let's say I pumped in hydrogen and iodine. Oh, and this is a little technique, you guys, I'm not gonna use it too much here, but if you guys go on to AP Chem and others, you'd use a technique called ICE. I stands for initial. You guys notice this is the initial concentration. So when I started out, I didn't start out with any hydrogen iodide. It's kind of like this. You guys remember with this, I just kind of started out by putting the balls on this reactant side and then some went right forward. So initially the concentration of hydrogen iodide is 0. Well then, when you guys agree, some of it is going to react and form the product. So then we could figure that out. I don't want to get too much into the math involved, so I'm going to make this easy. But then eventually it's going to reach equilibrium. That's what E is. So I is for initial, C is for change, E is for equilibrium. And then at equilibrium, the concentrations are going to stay constant. So let's say at equilibrium, let's say I've reached equilibrium, okay? And I know it because the colors staying the same. And let's say I'm able to separate out the different gases in here. And you guys, what gases are in here in a reverse reaction? Aren't all the gases present? They're all present. So let's say at equilibrium, I have 0.2 molar of my hydrogen gas in there. And let's say I was able to isolate and I have 0.2 molar of my iodine gas. And then hydrogen iodide, I have 1.6 molar. Now don't worry about how I got those. Let's just say we determined that experimentally. We were able to separate those out, okay? Now you guys remember, with what I'm going to expect you guys to be able to do is calculate what's called the equilibrium constant. You guys remember what's constant? Regardless of how much I use, remember, it's always the ratio of products to reactants. So here's how you guys are going to write. You guys are going to be expected to write what's called an equilibrium expression. So KEQ, you guys remember it's the concentration of the products. Look at my products here. It's hydrogen and iodide. You guys remember what you got to do? You got to raise it to a power equal to the coefficient. So I take the concentration of my hydrogen iodide at equilibrium and square it over the concentration of my reactants. I got the concentration of H2. Notice I'm not raising it to a power because the coefficient's 1. And then I multiply that by the concentration of iodine. Once again, that's raised to the first power, so I don't indicate that. So if I wanted to calculate the equilibrium constant for this reversible reaction, what would I do? I would plug into this is called the equilibrium expression for this reversible reaction. I plug in the equilibrium values. So these are the concentrations of equilibrium. What's the concentration of HI? I just gave it to you, don't worry about it. I put in 1.6. What do you have to remember to do to it? You got to remember to square it over the concentration of hydrogen, which was 0.2, times the concentration of iodine, which was 0.2. And I plug that in, and I believe I did this before, and I believe you get 64. So this, you guys, I will say this is called the equilibrium constant. The only thing that changes the equilibrium constant, you guys, is the temperature. The temperature, you guys remember with Le Chatelier's principle, we actually haven't covered that yet. But anyways, the temperature can affect the equilibrium. So it's not quite proper to say the equilibrium constant for this reaction is 64. I'd have to say it's 64 at 445 degrees Celsius, because if you change the temperature, that's the one thing that can alter your equilibrium constant. You guys, the equilibrium constant actually tells you a lot. You can actually look in a table, a book for different chemical reactions, different reversible reactions, and you can look up equilibrium constants. What does that tell you? So here's what I want you guys to see. If you have a large K value, and how I'm going to define a large K value if it's greater than 1. You think about it, what side of that reversible reaction is favored? What am I going to have more of when I see that it's a 64? You guys, you have to look at the math involved. You guys got to remember, the equilibrium constant, how is it determined? It's the ratio of products to reactants. So how are you going to get a number here that's bigger than 1? What does that have to tell you? Wouldn't that tell you that your numerator on top has to be a larger number than your number on the bottom? That's the only way you're going to get a number greater than 1, right? If you take a large number divided by a smaller number. And what's on the top in the numerator? That's our products. So when you see a number of a quote large K, that means what we're going to say is greater than 1. What that would tell you is, in this reversible reaction, the product side is favored. Basically, when it reaches equilibrium, you're going to have a greater concentration of products than you do of reactants. And now think about the reverse. What about if you get a value that's a small k? Because you can get values that's like 1.6 times 10 to the negative 5, which is like 0.000015. Very, very small numbers. Well, think about it. How would you get a number less than 1? Wouldn't that imply that the denominator on the bottom is a bigger number than your numerator? And what's the values on the bottom? That's your reactants. So if you ever look up for a reversible reaction, you see it has a small k value, what does that tell you? It tells you that the reactant side is favored. Reactants are favored. Okay. One last thing, guys. Let's say we change some things up. And in this, okay, let's say it's to reach equilibrium, but then, you guys, let's say I change some things up and then I put in some more hydrogen. You know what? Let's not even say that. I'm going to say, you know, remember we started with 1 mole of hydrogen, 1 mole of iodine. You guys can see it's kind of faded now because, and that's not surprising. Why is this really faded? You guys see it's kind of hard to even see the purple there, because what side of this reverse reaction is favored, guys? The fact that it has a number greater than 1 tells you the product side is favored, and therefore there's very little iodine here. Okay, so let's say I put in some more iodine. Okay, so now what I'm going to do is, let's say I already have 1 mole of iodine, but let's say now add 2 moles more iodine. Okay, so I'm going to do that over here. Okay, now wouldn't you guys agree? So I added some more iodine. Okay. It's kind of like this, guys. Kind of like if I just put some more balls into the, into our golf cart. Okay. So, you guys see? Okay. So you guys see how it's more purple. So I added some more iodine. Okay. All right. And you guys think about it. Once again, what's going to happen? Eventually, what's it going to do? It's going to reach equilibrium. So then let's say it reaches a new equilibrium. Okay, it's going to reestablish equilibrium, and now let's say I'm able to pull some different the different substances out. Let's say I'm able to separate out the hydrogen, separate the iodine, and separate out the hydrogen iodide. Okay, so I pull those all out, and then once it's reached equilibrium. So then the question is, let's say then I plug the new values in, because these values would all change. All these values that were there, they're all going to change, because I added more iodine, right? So I plug the new values in, and what do you guys think? What do you guys think you can predict about the KEQ under this new situation where I added more iodine? It's kind of a trick question, guys. What's the KEQ? It's still 64. These values aren't going to be the same. It's not going to be 1.6, 0.2, but what's going to be the same? Not the values, not the amount or the concentration of reactants products, but the ratio. That's what they found chemically. The ratio of products to reactants is going to be the same. So it's still going to be 64. And you guys, when will it stay 64? It will always be 64 for this reverse reaction. You guys remember the only thing that affects it? When you're at 445 degrees Celsius. You guys, that's why it's called the equilibrium constant. Very powerful tool to help us to understand, reversible reactions. You guys, at this point, you know what? I'm gonna make one other point. You guys put this. One other point is here. Make a note here. You guys just put in your notes. Note. Only include gases and aqueous substances in the equilibrium expression. Once again, you guys, what do I mean by equilibrium expression? That's this right here. This is called the equilibrium expression, where you have the ratio of the products to the reactants raised to the certain power. The only thing you guys are going to include in here, once again, are gases and aqueous. And here's the reason why, guys. Because those are the only ones, those are the only phases whose concentrations can change. You guys think about this. Guys, let's say I have some water here. Well, let's go with this. One sec, guys. Let's say I had some a liquid. You guys, right? When you guys agree, water is a liquid. Let's say water took part in a chemical reaction, and some of the water was consumed. So I had some. Let's say I have 100 milliliters of water. Some of the water was consumed. Okay. Let me ask you guys: did its concentration change? In fact, does it even make sense to talk about the concentration of a liquid? What would I say is the concentration of this water if it's pure water? When I say it's 100%, some of it got used up, right? Let's say some more of it gets used up. Now what's the concentration of the water? Isn't it still 100% water? The concentration doesn't change. The concentration is a constant. And so for a pure liquid, if the concentration is a constant, that value already gets incorporated into the constant. I know it gets a little confusing with that, but that helps explain why we don't include pure liquids in the equilibrium expression. Also, what we do not include in the equilibrium expression is solids. Think about this. Does it make sense to talk about the concentration of paper? You guys already know what does paper react with. Don't say fire. You guys know it reacts with oxygen. Let's say some of the paper reacts, right? So obviously, what changed here? Didn't the amount of paper change? Don't I have less paper than I had before, right? Because some of it reacted. But did the concentration of the paper change? No, the concentration of this paper is still whatever concentration it was before. You'd say it's 100% paper, okay? Let's say more of it reacts. Once again, I have less paper. Did the concentration change? No, the concentration of solids stays constant. Once again, that's already incorporated in your equilibrium constant. The only substances that you guys will include in an equilibrium expression are gases and aqueous solutions, because those are the only ones whose concentrations can change. All right, guys, I think that's enough. Thanks for sticking it out with me. We'll see you next time.